Let's now take a look at how k-means clustering is done with R. So the first thing to do is I've created some files that you would need to uh, get in. So for example, you've got dar2ed-k-means-plot.r. Okay, this function will allow you to generate the plot from which you can decide upon the value of k. And this one you've already used for knn, dar2ed-scale-many.r. Of course, just like knn, this requires us to do scaling. So these are two functions that you will need to get in. So for example, dar2e.k-means.plot function is here. This is a function that I wrote just so that you can look at the plot easily. And so you've got both of these functions loaded in here, and you have to click on the source button on top to source them in to your system. There. Okay, you've already done this for knn, so you're familiar with this process by now. Okay, so here the data set that you're going to use is hwcluster.csv. This has the same data that I've been discussing till now, the age and height data. And first of all, as we already know, you need to scale the data so that you can use it, so that a particular attribute doesn't dominate all your clustering decisions, right? So dar2ed.scale.many, hw, and the first two columns. The data set has only two columns. Okay, and here we are saying do the k-means. K-means is the function to do the k-means clustering. K-means hw3, 4. Why is that? Because 3 and 4 will contain the scaled attributes. We don't want to use the unscaled attributes at all. Okay, so we're saying k-means, that's the function, which data to do clustering on. So hw, 3, 4. So we want to use only those columns. How many clusters? 2. Okay, so that's it. Fit will now contain our clustering decision. So if you type fit, then you see the clustering model that the system has generated. And there's a lot of information here. Okay, so we asked for 2 clusters, and here are the cluster means of the 2 clusters. Okay, of course, we use the standardized attribute. So you got age underscore z, height underscore z. For the first cluster, the average age underscore z is minus 0.882 and the average height is minus 0.940. Of course, we saw this earlier as well. And these are the 2 means for the second cluster. Okay, and then it's also giving you this clustering vector telling you of all the cases in your data set, each case belongs to which cluster, right? So it just so happens that the first 6 cases belong to cluster 1 and the next 6 cases belong to cluster 2. But in general, it won't be like this. Okay, this just happens because our data was so regularly organized, right? Otherwise, you might see something like 1, 2, 2, 2, 2, 1, 1, 1. They could all be mixed up. Okay, it just happens to be like that. So this clustering vector tells you for every row of your data to which cluster it belongs. Our data has 12 rows. The first 6 belong to cluster 1. The next 6 belong to cluster 2. Okay, then it's telling you for each cluster what is the within SS for each cluster. We already know that the within SS for the first cluster is 0.9566. We calculated that earlier, and the within SS for the second cluster is this, right? So if you had more clusters, it would have given it to you. And what it's showing you here is the addition of all the within cluster sum of squares, okay, divided by the total sum of squares, not the addition of these two. But remember, there are 6 with this and 6 with this, right? 6 with this mean and 6 with this mean. Okay, so if then you calculate that, what you get is 90.7. This is telling you that 90.7% of the variability in the original data is still retained by this clustering solution that has only 2 clusters. Okay, so that's really the essential part of the output. So you'll perform the clustering and then you look for this number. If this number is decent, then you know that your clustering solution has been quite effective. For example, on the other hand, suppose you did 2 clusters and you found that it retains only like 20% of the variability, then you say, no, it's not doing the job, right? It's reducing the complexity, all right, but it's losing too much of the variability in the data to the extent that it's not representative anymore. Okay, so now I'm going to take the approach of how to generate that plot from which we can choose the k value. Okay, so this function is what I'm using here, dar2ed.k-means.plot hw1, 1 : 2. Now this function, the way I've written it, it does the normalization and does everything. So you don't need to do any normalization to plot this. Okay, we are using this only to choose the value of k. So just say that I want to plot a cluster based on the first 2 columns, and we are not using normalized columns because this function automatically takes care of that, right? So the moment you do this, it shows you the plot. It says, okay, number of clusters is this, and this is the total error, the sum of the within SS for all the clusters you have. From this, I would look and say, okay, I like 2 because that is what is giving me the maximum. The change from 1 to 2 gives me the maximum benefit. Okay, so now that you have that, we can then go back and say, okay, now I know I need 2 clusters. I'll repeat the code for getting 2 clusters, just like we did first. Okay, and then here I'm just saying HW $cluster equals fit $cluster. In other words, in your data set, if you want to add a column that tells you to which cluster each case belongs, then you can do this. Okay, so then it will tell you for every row, okay, that row belongs to cluster 1, this row belongs to cluster 2, that other row belongs to cluster 5 if we had several clusters. Okay, that's the idea of this. Okay, so you're adding a column to denote the cluster membership of each row. Okay, now this example is what you will be working through in your lab, which I'll ask you to perform. I'm just quickly going through the code here. So once again, here we are using the autompg.csv dataset, and we want to create clusters of automobiles. Okay, and the first column is not useful. It's it's just a name of the auto. 2 to 7 contain the remaining attributes. Now, incidentally, remember when you're doing cluster analysis, there is no target attribute because it's not a predictive model, right? So we are using all the attributes other than the first attribute, and we are doing a dar2ed.k-means.plot. So once again, you see the familiar curve of reducing error. So in this case, I think I chose to use 4 clusters. You could have gone with 3 if you liked, because there is still a good drop between 2 and 3, and I think between 3 and 4, and some may say between 4 and 5. Okay, subjectively, I'm choosing 4. Okay, and I'm generating the clustering with the 4 cases, with 4 clusters. Okay, and I noticed that this 4 cluster solution reduces the complexity from, I think this has 240 rows to just 4. Phenomenal reduction in complexity, and it is still retaining 79.4% of the variability which the original data had. Okay, so that looks like a really powerful clustering solution as far as our goals are concerned. Okay, and here are the so I did auto $clusters, fit $cluster. Okay, and then fit $centers gives you the cluster centers, right? Remember we said here are the centers of each of the clusters, this part. Okay, so it's saying there are 2 clusters and these are the centers of the 2 clusters, meaning the center of age and center of height, center of age and center of height for the 2 clusters. So that's what we are getting here. Okay, so auto $clusters, fit $cluster, that's just assigning to every row which cluster it belongs to. And then fit $centers, I'm rounding it off to 2 decimal places. Okay, so here are the 4 clusters, and here are the centers. This is the mean scaled MPG for that cluster. This is the mean number of cylinders for that cluster, again standardized and so on. Okay, so now the next thing to do once you have done clustering is to give a meaningful interpretation for each of the clusters. Okay, now one thing to remember is that each of these values is a standardized or normalized value. Okay, so if the value is negative, that means it's below average of the original value, right? So for example, the cluster center of the first cluster consists of cars with lower than average miles per gallon, right? In fact, significantly low, 1.15 standard deviations below the mean MPG. Okay, it's got high number of cylinders, 1.48 standard deviations above the mean, and again high displacement, uh, fairly very high horsepower, very high weight, and low acceleration. That's what you'd expect, right? It's a heavy, big vehicle uh, with lots of cylinders, but still proportionately more weight and so on. So its acceleration is below the average by about a standard deviation, right? So that represents the characteristics of one cluster. So what you want to do is to take the clusters and give them an interpretation from the real world, right? So I might say that the first cluster consists of big cars, right? Big lumbering cars with lots of cylinders, low fuel efficiency, low acceleration, and high horsepower, but even high weight. Okay, so the second one consists of cars which have almost one standard deviation higher than the mean in terms of their fuel efficiency. Okay, low number of cylinders, low displacement, which means a small engine, low horsepower, light, and good acceleration. All right, so you might say that these are green cars, small cars, might call them as green. Okay, so you've got this should be here. This is the third cluster. This should be pointing here. Okay, so these again have somewhat lower miles per gallon, etc. I chose to classify them as compact. Oh, okay, this was the fourth one. I called this the compact, and I called the third one as the salon car. Somewhat big cars, but not hulks like this. Low fuel efficiency and so on. Okay, so the idea is to look at the cluster and give it some meaning in your context. Not just look at it as a number, but say, okay, in the real world, what does this cluster actually represent? Okay, so that's the whole idea of cluster analysis. I'll be asking you to perform a lab on cluster analysis that will walk you through the details of this particular example that I had done here.